In this video, we work a few example problems in which we use algebraic manipulation, partial fraction decomposition, and known Laplace transforms to compute inverse Laplace transforms. This is our first example, but just as a review, the Laplace transform of 1 is 1 over s. The Laplace transform of e to the at is 1 over s minus a. The Laplace transform of t to the n is n factorial over s to the n plus 1. The Laplace transforms of sine and cosine of kt have s squared plus k squareds in the denominator, and the sine has a k in the numerator, and the cosine has an s in the numerator. The hyperbolic cosine and sine of kt have s squared minus k squared in the denominator, and here the hyperbolic sine has a k in the numerator, and the hyperbolic cosine has an s in the numerator. Now we're taking inverse transforms in this video, so we're going to go from this side to this side. So if the Laplace transform of these functions is equal to these functions, the inverse Laplace transform of these 7 functions is equal to these 7 functions over here. So if I am looking at something like this, I definitely don't have anything that has a cubic polynomial in any of these denominators. But if I do some partial fraction decomposition, I can probably write this as a linear combination of expressions that look like what I have here. Now notice that the degree of the denominator is greater than the degree of the numerator. So we are all set to get started with partial fraction decomposition to rewrite this. Now, the first thing that we need to do if we're using partial fraction decomposition is we need to rewrite that denominator in factored form. And of course, this is provided that the degree of the numerator is less than the degree of the denominator. If the degree of the numerator is greater than or equal to the degree of the denominator, you always want to divide first, but that probably won't be appropriate here whenever you are working with f of s, because if the original function f of t is piecewise continuous and of exponential order, this expression should go to 0 as s goes to infinity. So most of the time, the degree of the numerator is not greater than or equal to the degree of the denominator. Okay, so you've got a numerator that looks like this, and I have this expression down here, and I want to factor it as much as possible so that I can do partial fraction decomposition. So I would factor out an s first, and then I'm left with s squared minus 2s minus 3. And this factors further to this expression. If I have s squared minus 2s minus 3, I can factor that this way. I need 2 numbers that multiply to give me -3 that add to -2. -3 and +1 will work. -3 times +1 is -3, and -3 plus 1 is -2. So this is equal to this, and that means we can use partial fraction decomposition from here. So I've got 2s squared plus 3s minus 3, and I'm dividing by this expression. And I've got 3 linear factors. None of them are repeated. So the partial fraction decomposition looks like this. It's a over s plus b over that second linear factor plus c over the third linear factor. And we want to multiply by the LCD, which is always the original denominator. And since we have linear non-repeated factors, it's going to be really easy to solve for a, b, and c. We'll just choose the values of s that make each of those factors 0, and that's going to be enough to allow us to find the values of a, b, and c. So when you multiply by that LCD, the denominator should reduce completely. So the s's reduce here, the s plus 1's reduce, and the s minus 3's reduce. The s's reduce here, the s minus 3's reduce here, and the s plus 1's reduce there. And so now you've got this 2s squared plus 3s minus 3 equals a times s minus 3 times s plus 1. And then you can just keep going. And now we just choose the value of s that would make each of these factors equal to 0. So I'll choose s equals 0 first. Then we'll substitute that into both sides of the equation, and that will allow us to find the value of one of our variables. If s is equal to 0, I've got 0 plus 0 minus 3, so a -3 on the left-hand side. And on the right-hand side, I'll have a times -3, because I'm replacing s with 0, times 1. And this is b times 0 plus c times 0, so those guys are gone. So we've got -3a equals -3, so a must equal 1. Similarly, I can let this factor equal 0 by choosing s equals 3. Then in that case, I'll have 2 times 3 squared. So 2 times 9 is 18. And then I'm adding 3 times 3, which is 9, and I'm subtracting 3. And then over here, when s is equal to 3, I've got a times 0, so that's gone. And when s is equal to 3 here, I have c times 0, so that's gone. So the only non-zero term is this one in the middle. So I've got b times 3 plus 1, which is 4. So I've got 18 plus 6 is 24. And 12 times b on the other side. So b must be 24 over 12, which is 2. And then the only factor remaining is a s plus 1. That's 0 when s equals -1. So plug in -1 over here. -1 squared is +1. So we're going to have 2 plus 3 times -1, which is -3 minus 3 equals, when s is -1, this is 0 and this is 0. And I have c times -1. -1 minus 3 is -4. So I have -6 plus 2 is -4, and that's equal to 4 times c, so c must be -1. So f of s is actually equal to a over s plus b over s minus 3 plus c over s plus 1, where a is equal to 1, b is equal to 3, and c is equal to -1. So a is 1, b is 2. I think I may have said b was 3 just a second ago. I meant b equals 2. And c is -1. Oh, and that's easy. Now we can just take the inverse transform. That's going to be an exponential. That's an exponential. And that will be 1 because of this rule and this rule. So in that case, f of t is the inverse transform of these guys. So we've got 1 plus 2, and the inverse transform of 1 over s minus 3. Well, that's, since a is equal to 3 there, we're going to have e to the 3t. And then we're subtracting to bring that constant down. And on this one, we've got s minus a, where a is equal to -1. So this will be e to the -1t, or -t. And that's our f of t in that case. Okay, so that was our first example like that. Let's do one more. At least one more. So let's try this one. I've got f of s equals 5s squared minus s plus 2, all divided by s cubed plus s. Okay, now on that one, the degree of the numerator is less than the degree of the denominator, so we can go straight to the partial fraction decomposition. Always start by factoring that denominator as much as possible. When you factor out an s, you're left with an s squared plus 1, because s times s squared is s cubed, s times 1 is s. Now, this s squared plus 1 does not factor to s plus 1, s minus 1. This is a sum of two squares. A sum of two squares does not factor further. That is an irreducible quadratic factor. So when you set up the partial fraction decomposition, since you've got a linear factor and an irreducible quadratic factor, what you're going to end up with is a constant over the linear factor. That's what happens for all of our linear factors. Plus, for an irreducible quadratic, a constant times your variable plus a constant over the irreducible quadratic. Now remember that variable is not an x anymore, it's an s this time. So that's what's appropriate here. Now we want to find the values of a, b, and c that cause this expression to equal this expression, and that's going to require multiplying by the LCD, which is the original denominator. So if we take this guy, and we multiply by s times s plus 1. I'm going to skip some steps. Normally I don't, but I'm running out of space. So if I take this and I multiply by this, the denominator will cancel and I'll just end up with the numerator. Now, if I take a over s and I multiply by s times s squared plus 1, the s's will reduce, but the s squared plus 1 won't. And if I take this and multiply by s times s squared plus 1, the s squared plus 1s will reduce. So I'll still have bs plus c in the numerator, and then I'm multiplying by an extra s. Then we want to distribute our a and our s here. So we have as squared plus a plus bs squared plus cs. And then since s to the 0, s to the first, and s squared are linearly independent functions, the only way that this polynomial in s equals this polynomial in s is if the coefficients are equal. So we can find a, b, and c by setting the coefficients equal to each other. So I want to use a little bit more of the bottom of this piece of paper here. So I want to group like terms in s. So I've got to get my s squared terms together. I've got an as squared and a bs squared, so that's a plus b times s squared. And then I've got a constant times s here, and then the constant term. The only way these two polynomials are equal is if the coefficients are equal. And again, that's because of the linear independence of the functions. So a plus b has to equal 5. The coefficient of s must equal the coefficient of s on this side. That's an implied -1. So c must be -1. That's nice. And the constant a must be equal to 2. That's nice too. So we've got a and c. We just need to find b. Well, if a plus b is 5, then b is equal to 5 minus a. And if we know that a is 2, we're going to get b equals 3. So I've got a is 2, b is 3, and c is -1. And that means that our partial fraction decomposition is this. So our f of s was over here. It was this, and we said that f of s is equal to a over s, and a happened to be 2. So we have 2 over s plus bs plus c. b is 3, so that's 3s plus -1 or -1 over s squared plus 1. Okay, now I don't have a rule that has this a constant times s plus a constant in the numerator here. When I look at my list, let's look at those on the list. You to ignore all this other stuff from before. If we look at that list, we've got an s over s squared plus k squared and a k over s squared plus k squared, but we don't have a linear combination of those. So we're just going to have to break this up into 2 pieces. We're going to separate the numerator. So this is 2 over s plus 3 times s over s squared plus 1. S over s squared plus 1 is going to be a cosine. And then this is a -1 over s squared plus 1. And 1 over s squared plus 1 is a sine. If k squared is equal to 1, k is equal to 1. So this is actually going to be a sine of t. This is a cosine of t, and that's just going to be a 2. So when we take the inverse transform of this piece, or of this guy, we end up with 2 plus 3 times the inverse transform of that, which is cosine of t. And then we're subtracting the inverse transform of that piece, which is sine of t. And if you're not sure, you're like, how are you getting that again? So I'm looking at this and I'm pattern matching it to this. And I'm saying, well, k squared is 1. So that means k is always the positive square root, so k is 1, and k is 1 here as well. And I have to have a 1 in the numerator have a k in the numerator if there's a k squared down here, and with 1 we were already all set on that one. So this is cosine of kt where k is 1, and that's sine of kt where k is 1. So that is that one. Okay, so let's do one more example. I feel like those were almost too straightforward. They were just too easy. Usually there's a little bit more work to do, isn't there? So let's make sure we get an example that is a little bit more challenging. Okay, so let's say I want to compute the inverse transform of s over s cubed plus 2s squared plus 4s plus 8. Someone says, just compute the inverse transform of that. Well, in order to do that, I just need to factor that denominator as much as possible and then use partial fraction decomposition again. So I'm going to look at this cubic polynomial and see if it factors nicely. Since it has 4 terms, I'm always interested in seeing if factoring by grouping will work. So I'll group the first 2 terms and the second 2 terms and hope that when I factor out something that these 2 guys have in common and that I factor out what these 2 guys have in common, I'm going to be left with a factor that is common to both of those expressions. So let's see if that actually works here. When I look at these 2 guys, if I factor out an s squared, I'm left with, well, s squared times s would give me an s cubed. S squared times a 2 would give me that 2s squared. Okay. Question is, if I factor out a common factor from this, am I left with an s plus 2? I think I am. If I factor out a 4 there, 4 times s gives me 4s, and 4 times positive 2 gives me that 8. So then when I look at this group, and I ask myself, what do they have in common? They have the s plus 2 in common, so I can factor that out from the groups. And then I'm left with an s squared plus 4. Okay, so that's my denominator. I've got s over s plus 2 times s squared plus 4. And that is a linear factor and an irreducible quadratic factor. So I'll write that as a over my linear factor plus, for the irreducible quadratic, a constant times your variable plus a constant over the irreducible quadratic factor. Then we multiply by the LCD, which is always the original denominator. And then reduce, those denominators should all be gone. If they're not gone, excuse me, you have not chosen the least common denominator. So we'll have s in the numerator over here, and then a times the quantity s squared plus 4 over here. And then we'll have bs plus c times the quantity s plus 2 over here. Now we can find the value of a without coming up with that system of 3 equations and 3 unknowns, because we can set s plus 2 equal to 0 and solve for s. If s is equal to -2, this factor would be 0, and that will allow us to solve for a. So I'll let s equal -2, and I'll substitute into this equation. Then I'll have -2 on the left-hand side equals a times -2 squared is -2 times -2, which is 4, plus 4. And then if s is equal to -2, this is 0, and so that guy is gone. And so I've got 8a equals -2, so a equals -2 over 8, which is -1/4. Now to get b and c, well, I need s squared to equal -4, which would mean s is equal to plus or minus 2i. Now, I told you before that s could be a complex number, but we don't tend to solve systems of equations that way, especially if we haven't had complex analysis yet. So let's not solve that way. Let's solve this by finding a system of equations. So since I have an irreducible quadratic factor, s squared plus 4, in order to solve for b and c, I'm going to distribute my a here. And then distribute over here, we'll have bs squared. First times first, outer times outer is 2bs. Inner times inner is cs, and last times last is 2c. And now I want to collect like terms in s squared. So I've got or collect like terms in s. So I've got an a plus b times s squared there. And then I want to collect my s terms. I've got a 2b plus c multiplied by s. And then my constant terms are 4a and 2c. So that has to equal this polynomial on the other side, which is a 0s squared plus s plus 0. Now the only way these are equal is if the coefficients are equal, because we know that s squared, s, and s to the 0, which is 1, are linearly independent functions. So the only way these guys could be equal is if the coefficients are equal. So the coefficient of s squared on the left-hand side must be equal to the coefficient of s squared on the right-hand side. And the coefficient of s on this side must be equal to the coefficient of s on that side. So 2b plus c must be equal to 1. And the constant term on that side must equal the constant term on this side. So we've got 3 equations and 3 unknowns, and we need to solve for a, b, and c. You basically want to get this system of 3 equations and 3 unknowns down to 2 equations and 2 unknowns in order to solve it. So I think what I'll do is I will write everything in terms of, let's say, a and c. So let's figure out what b is in terms of a. From this first equation, we have b is equal to negative a. And then if I'm writing this equation in terms of a and c, replacing b with negative a, I have negative 2b plus c is equal to, or negative 2 a, plus c is equal to 1. And here I've got 4a plus 2c is equal to 0. Well, in order to solve that, I need the coefficients of a to b equal, but with opposite signs, equal in magnitude, but with opposite signs, or the coefficients of c. So we can multiply this equation by positive 2, and that would get rid of the a's if we added them together. So I think I'll do that. So I have negative 4a plus 2c equals 2, and 4a plus 2c equals 0. If we add, we get 4c equals 2. And that means that c equals 2 over 4, which is 1/2. Okay, if c is equal to 1/2, then we can use the fact that c equals 1/2 to find either a or b. Well, since c is equal to 1/2 and 4a plus 2c is equal to 0, we've got, if I divide that equation by 2, 2a plus c is equal to 0. So 2a is equal to negative c, which is negative 1/2, and that means a is 1/2 of negative 1/2, so that's negative 1/4. And b is the opposite of a, so b is positive 1/4. Oops, sorry, I was off the page. Okay, so now I've got my a, b, and c. I was asked to compute the inverse transform of s over s cubed plus 2s squared plus 4s plus 8. I'm still not sure that this was the most complicated one that we could do, but that's okay. Oops. And that turns out to be a over s plus 2, where a is negative 1/4, plus bs plus c over s squared plus 4. So b is 1/4, and c is negative, or no, c is positive 1/2. Okay. Now this one I can take the inverse transform immediately. That's a negative 1/4 times an exponential. Since we're subtracting negative 2 here, a is negative 2. So we're going to have a negative 1/4 times e to the negative 2t there. Now this looks kind of like the formulas in our table, but it's not quite right. We've got, oops, that's the wrong one. So many pages of this stuff now. There it is. That's what I was looking for. We've got an s over s squared plus k squared here, and we've got a k over s squared plus k squared, but we don't have a linear combination of s and a constant. So we're going to have to split this up into 2 terms. So we end up with this. This first piece is -1/4 times e to the at, where a is -2. And then here, I want to write that as 1/4 times the inverse transform of s over s squared plus 4. And then I'm going to factor out that 1/2 and temporarily leave that numerator as a 1. But then I'm going to think about what the numerator would have to be. So remember, if this is k squared equals 4, that means k is equal to 2. And I'm supposed to have a k over s squared plus k squared here. So I need a 2 in the numerator. Well, I can get a 2 in the numerator. I just have to multiply by 2. That's legal as long as I also divide by 2. So that's just multiplying by a well-chosen 1. We make it look exactly like what we want it to look like. And that's legal as long as we also compensate for that. So this is going to be an s over s squared plus k squared. That's a cosine of kt. This is k over s squared plus k squared. So that's a sine of kt. In both cases, k is equal to 2. So we're going to end up with this -1/4 e to the -2t for this first piece. And then we had 1/4 times cosine of 2t plus 1/4 times sine of 2t. What's a 1/4? And I think that's it for our practice with partial fraction decomposition and those 7 basic Laplace transforms.